Alright, this is our last video for this section. We've been talking about piecewise functions. We saw the tax bracket in the last video. Here we're just going to talk about some more general ideas of particular kinds of piecewise functions. In particular, we're going to talk about a step function. A step function is a function whose graph is a set of disconnected horizontal line segments, i.e. stairs or steps, that are increasing or decreasing. And actually, our tax bracket is an example of that, right? As you go to higher incomes, you keep stepping up in your tax percentage. So that's an example of a step function. We're going to look at another mathematical version or specific mathematical example of a step function called the greatest integer function. The greatest integer function is the function for whom each range value is equal to the greatest integer that is less than or equal to the corresponding domain value. So for example, f of 3 is 3 because the greatest integer that is less than or equal to 3 is 3. The greatest integer that's less than or equal to 3.4 is also 3. The greatest integer that is less than or equal to 3.9 is also 3, right? So as the domain value gets larger, you can stick with the same range value until you get to the next integer. Once you cross over 4, now the greatest integer that's less than or equal to 4.302 is 4. Okay? And we're gonna draw a graph of it and see it in a minute here. But this function has a special notation. It's this square bracket on the sides, and these double lines are a specific aspect of it. Okay, so it is, you should draw it with these double lines when you do it by hand. That is the greatest integer function. Okay, and it would be read as f is equal to the greatest integer that is less than or equal to x, or you could just say f is the greatest integer function. So let's graph the basic parent version of the greatest integer function. You also will remember I mentioned this function briefly at the beginning of this, or excuse me, not this section, but the last section on families of graphs. We had this step function here. So I showed it to you briefly earlier in the unit. But anyhow, let's go to graphing the step function, greatest integer function. Well, if we don't know what a function looks like, we can always make a table of values. So I'm going to make a small table of values here. We'll have the x values, and then the y values are the greatest integer that's less than or equal to x. So if we start with something really basic like 0, the greatest integer that is less than or equal to 0 is 0. 0 is equal to it, so it counts as being less than or equal to. So at 0, we have the point 0, 0. If I plug in different integers, though, I'm just going to keep getting the same results, right? The greatest integer that's less than or equal to 1 is 1. The greatest integer that's less than or equal to 2 is 2. So if I just plug in integers, I get all these points, and it's not very interesting or exciting to think about. It looks like I'm just going to draw the identity function. So I have to look at values that are in between these values. So let me take 0.5, for example. The greatest integer that is less than or equal to 0.5 is 0. So if I were to zoom in here, then I know I have a point right there. At point x equals 0.5, I have the y value of 0. If I said x is 0.9, the greatest integer that is less than or equal to 0.9 is 0. So at x equals 0.9, I have another point right there. Right? And if I said 0.99, my greatest integer that's less than or equal to 0.99 would be 0. 0.9999, right? They would keep being 0, and it would all be 0 until I actually cross over and hit x equals 1. And then I would jump up to y equals 1. So all these x values, the greatest integer that's less than or equal to it is 0. So I keep having 0 for my y coordinate all the way through here until I actually arrive at x equals 1. At that point, I have to jump up to y equals 1 because the greatest integer that's less than or equal to x equals 1 is y equals 1. So I'm going to get infinitely close to x equals 1 but never actually reach it. So I'm going to draw that line and put an open dot there and say that at x equals 1, I'm not actually going to be on this line. I'm going to jump up to y equals 1. But as I keep going forward, if I were to think about x equals 1.5, the greatest integer that's less than or equal to 1.5 is 1. So at x equals 1.5, my y value is 1. And that's true at 1.2, at 1.7, at 1.9, at every value going up until I reach x equals 2. When I get to x equals 2, I have to jump up to y equals 2. So I'm going to keep getting infinitely close to it, but never actually arrive at x equals 2. And we're seeing this idea applied that we've been talking about, this getting infinitely close thing, but don't get caught up in that. The point is, when I actually arrive at 2, that's when my y value has to jump to 2. And every y value is going to keep being 2 as I get small 2.1, 2.3, 2.4 until I reach 3. When I actually get to 3, I have to jump up to y equals 3. And then I'll have 3.1, 3.4, 3.9 until I reach 4, and then I jump up to 4. And we can see this value, or we can see this pattern keeps repeating itself, right? And so this is my greatest integer function. It's worth noting, negative numbers are integers as well. This pattern will continue exactly the same on the left side. And then this is our graph of the greatest integer function. So this is the graph of f of x equals the greatest integer that is less than or equal to x. So just one more example of a piecewise function. Now this one's kind of a weird one because the graph is in pieces, but the rule for the function is a single rule that applies to every single x value. So it's kind of a weird one where it's defined with one rule, but the graph is in infinitely many pieces, right? And this would continue on, right? These stairs would continue on forever. So you can see why it's called a step function. That's really simple and clear. And this is a particular example of a step function. In the homework, they're going to ask you to do some transformations on this, but it's the same rules. So if I added 1 outside, I'd move the whole graph up 1, right? So all the same basic rules will apply. So that's what you're going to be doing for homework, is practicing graphing piecewise functions, evaluating piecewise functions, maybe a couple of word problems here to apply them. But that's your homework on page 48, on page 48 in your physical textbook. And that is our section on piecewise functions.